Morning.
Good morning.
I'm preparing my talk for tomorrow.
Where are you talking tomorrow?
In New York,
What time is it at?
10 o'clock. You are innocent graduate students. You don't have to put up with any of that. It's funny, much of the theoretical physics is the same. So essentially a figure I drew in our course, but now it's research. See this figure? Nobody will understand what that figure is. So what we'll do today is just kind of, piano exercises in a complex plane. So a few typical calculations that one tends to do in applications in quantum mechanics, electromagnetism, wave mechanics. And they have to do with Green's functions and stuff like that, which we might get to, but we certainly get to in the other courses. So the strategy is always called residue calculus. As you can see, it requires a great deal of coffee. Now, the idea of residue calculus is that you take any function of a complex variable in a complex plane, and you pull out a simple pole or a multiple pole, meaning some power of an ordinary singularity at the function. And, this function is something like sine and cosine, so every so often goes through the zero. And every so often, if it's a rational function, it explodes as a pole. And you just pull out the residue or coefficient at that pole. And you do that by going to the Cauchy integral representation. And the result is that whenever you have if you can turn your integral into a contour integral, which I'll now show a number of examples of, then I can replace that contour integration by going around all the poles in a complex plane. Here there are 4. And for each one of them, what I have to do is I have to separate this function into a residue function times 1 over z minus z1, that pole, and evaluate the residue function at the pole itself. So it gets to be a sum of residues. And there are a few tricks. I did some integrals already using this technology. And here are a few things that in applications you often get exposed to. One of them is called principal value. So principal value integral has 2 versions. In the real plane, it's morally an integral over dx over x if the pole is at origin, make it simple, over some interval from minus a to b, which includes the origin. And principal value is defined as you get as close to the origin and you integrate that, because as long as epsilon is non-zero, that's a finite integral. And on the other side, you get as close from the origin. On the other side, they integrate the rest. So here is what it looks like. These missing parts, what you're omitting when you do this integration, you're omitting stuff between epsilon and origin on one side and on the other side. Now what happens when you have a pole On this side, x is positive, so singularity blows up. On this side, x is negative, so singularity goes down. And if you're close enough, these two integrals cancel each other exactly. One is positive, one is negative. They look the same. And that's why it makes sense to define this principal part. The singular part cancels, and the real part is what you call principal value. Now, that's a little bit iffy, this kind of argument, because, there might be some finite leftovers. Is this really exact? And again, the complex version of the world is much nicer. The truth in the complex plane is very simple. If you ever have a pole at origin, like this one, if this is z and this is complex plane, so we're looking at dz over z, we know that for that pole we can turn into a simple constant radius integral of arbitrarily small radius running on a circle. And that calculation gives us 2 pi I, because an I pops up while you're doing it from the converting dz into the angular integration. Now, this is same every place. So you actually allow it to split this into 2 half counters. You can run it from here and you can run it from there, and you can evaluate both. So you can discuss counters that involve half circles, not full circles, and 2 of them add up to the usual 2 pi I. So that's the trick of principal value. Now, I will evaluate a typical integral that we encounter in designing radars or whatever, in which we have a singularity on the counter. So this is now a little bit more complicated. It's an integral from 0 to infinity sine x over x dx. But here is a typical trick what you do to make a real problem complex. You say, well, first let me make this integral from minus infinity to plus infinity. And that you can do because both x and sine x are odd under x going to minus x. So just take 1/2. And let's now put this in a complex plane. And the sine, I know it's imaginary part of complex exponential. So this is an identity. We have just converted an integral on a real line to an integral in complex plane. Now in complex plane, this thing has only one singularity, which is at origin.
Wait, sorry. So you just replaced x with z, kind of?
Yeah. I replace every place x by z. That's legal because z is a real plus imaginary part, and this integral is just on the real part. So the imaginary part happens to be 0. That's this line down here that original integral is on. But once I've converted it into imaginary quantities, into complexified version, I can use the counter technology to move counters around and simplify this calculation.
Okay.
So far it's just an identity, right?
What is the e to the iz? That would be
well, remember the sine is the sum of I times e to the iz minus iz divided by 2, right? That was one of the Euler's formula which represents sines and cosines in terms of sums and differences of these things. In other words, if I write e to the I z, it has two parts. It has cosine of theta plus I sine theta, and imaginary part pulls out the sine theta.
Okay, yeah.
Imaginary part
So
pulls.
Yeah.
that means
Well,
that
you
z
know,
is a real
okay,
number?
e to the I theta is cosine theta plus I sine theta. So I can replace I sine theta, that's just the imaginary part of e to the I theta, right?
Right. Okay. So when you have to write the imaginary part of the numerator only, not the whole integral,
Well,
or z is real here, right? Is that
z
what
is
we're saying?
real. You know, we start with z being real. We just renamed it, but it has a zero imaginary component, so it's legal.
Okay. Are we going to add a imaginary component later?
Yes, because, you know, I drew the counter.
Okay. I just want to make sure because I'm just not familiar to me, so I don't know if that's like a legal maneuver. I guess it is, but if you
It's an
assume it's real,
identity. It's an identity because on this line here, z is x plus I times 0,
mhm.
right?
But that's only
So
valid for that line, right?
that's right, because integral is defined on that line.
Okay. So
You know,
we're
I'm
so
running
then
over that line from minus to
okay.
plus infinity.
Okay. So basically restricting this integral that you've written here, right? The z, the possible z for this integral. Only the real
Uh,
axis.
the definition of the integral integrate only over the real component.
Okay.
So even though I've renamed z, I say x is z, you know, they're identical on the line of integration.
So z is actually could be like a general z, but
Well, it
uh,
will become general z because I'll let myself move contour in a complex plane.
okay.
Remember, Adamar says that, you know, the truth in the real plane goes through the complex plane. So this is, you know, I'm showing you standard tricks how to take a real quantity and write it in terms of complex variables.
Hmm.
And once you've done that, this part is just identity, you know, nothing has happened. But once you have done it, you know, I just call x, I call it z because they are identical on the real line on the where the integral is defined.
Okay.
Once I've done this, I'm in a complex world, and I'm allowed to use the tricks of complex world, which is the most important one, is that the contours can be deformed and
Okay.
created. So now I do the next thing. I just cook up a contour, which we'll have to justify. So I cook up a contour integral, which has this form. For most of the real axis, it looks like, you know, this integral. For example, this part is literally running close, but I exclude the origin. I go, you know, little epsilon circle, arbitrarily small circle, and I stick a little runaround around here. And then the other half from minus infinity, I stick it here. So this is close to my desired integral, except this avoids the singularity at the zero. And then I stick to it a big semicircle, and I'll have to justify this. So this has a contribution around little contour. So this is a closed contour, but then it has parts of it. You know. So there is a this part here, there is a part from here going to distance r away. Let's call it CR. So that one starts here and goes away. Then there's a part that starts at minus r. I'll take r to infinity eventually. Minus r, to here. This is this part, CR. And now what I can do is I can evaluate all the little bits of this separately. So it's a counter, and within it there is no singularity. So I know that this sum of these integrals is 0. I know that much. Now, the part that we want to do is, going all the way here through the singularity. So let's just do bits. So what happens to the big integral here? So look at the semi-arc in the upper complex plane of radius r, integrated over IZ over Z dz. Again, what are we doing? On the real line, there's just a boring integral from minus infinity to plus infinity that has a little, a hump in the middle, which looks like that because, and we want to evaluate this. What we have done is we have related it to counter integral, which by Cauchy's theorem is 0. A part of it's our desired integral, and we have to just evaluate the extra parts we added by hand so that everything adds up to 0. So now this integral, it's a radial integral, so we go to polar representation where we, on this integral, we write Z on this integral is R, its magnitude I times theta, right? Now we have here dz over z. That combination, when we change the variables, R will cancel out. I'll get delta theta times I from parametric form of the integral semi. So that's what comes out from z dz. And what's left is e to the I real part of z times I times imaginary part that gives me minus here. And I'm integrating over a half circle in the upper half complex plane. So this thing, I will have to take imaginary part to get my integral. Imaginary part of I times something means that I have to take the real part of what's here. Real part of this is oscillatory integral, it's just phase. So the real part of this, the magnitude of this part is just 1. So nothing interesting happens here. Now this one is e to the minus r times sine theta, and only sine theta is 0 only at these little points. It's a positive number every place in a half circle. E to the minus r is huge, so this is an exponential of minus huge number. So this part is going to 0. And we find out that in the limit of taking a very large or infinite radius circle, this part of contour doesn't contribute to anything. It's a 0. Now, what about this little contour? Now we use the trick of understanding what principal values are in a half plane. If I have a circular contour around the pole, I can write it as a sum because it just has a radius and then it just has angle incrementing around on a circle. I can write as a sum of the integral from 0 to pi and then from pi to 2 pi. It's an integral, so I can write a sum of two integrals. And the first one and second one, they're obviously the same. This runs to pi I. So in complex plane, this half circle is easy to compute. But that's how principal value comes in. And this guy, in that limit, epsilon goes to 0. This is e to the 0, so that's a constant. And I just run around the circle, half of the circle, and that's why I get pi I. And why do I get minus pi I? Because this contour is going the wrong way, clockwise rather than counterclockwise. And you can interpret this in a residue calculus to be, the residue of this quantity. Residue always picks up 2 pi I, a residue of this thing, I, z, b, at z equals 0. The remaining part of the integral is the stuff that goes close from minus infinity or minus r to 0 and then from r to 0. So it's these two guys. Start to infinity, get close, integrate. Start close, go to infinity. So this is, and that by definition is the principal value. But now we have a result that the sum of all these guys should add up to 0. And going back to the original definition, the integral, which was 1/2 imaginary part principal value e to the I z over z dz is pi over 2. An integral from minus to plus infinity, this one looks innocent because there is no singularity on a real line, because there is no pole. X squared plus a squared, or a non-zero a never encounters a singularity. I can try the same trick. I can say, well, let me complexify it again by saying cosine x, let's call it cosine z, where on this line of integration z equals x because there's no imaginary part. I can complexify this, but this is going to be bad because if I take z large, then either one of these guys will diverge, so I can't. So this simplification looks like a bad idea. Cannot close. So instead of that, let's look at a different integral. And that's okay because the integral we want, if we can evaluate this one, we just have to take the real part of that guy. And it doesn't mean derivative, it's just a different integral. One is over a real variable cosine x, but now we replace it by a complex variable. So z has a magnitude and a phase. E to the I z is I to the r e I theta in the exponent. And now we replace the imaginary phase by a cosine, so that's real, but purely imaginary. And we get minus r times from I squared in a complex part, which we have done before. Repeating it 3 times is always useful. And as Mephisto says in Faust, do it 3 times always. So this thing, and we'll be taking real part, this is magnitude 1. Well, this one oscillates. Now, well, when we were looking at both e to the z, iz, and e to the minus z, either one or the other one is exploding depending where we went into the upper or lower half plane. If we had an imaginary number, now we only look at one of them.
Sorry, could I ask something?
Yep.
I was trying to think about what you wrote, the cannot close contour above. Maybe I'm thinking about real behavior, but isn't this cosine bounded? The range of it, I mean?
Yeah, the cosine itself, you're totally correct. On the real line, cosine oscillates. And, what makes this integral difficult, it oscillates between plus and minus 1. So the numerator wiggles up and down in a bounded regime. The numerator is just decaying like 1 over x squared as I go to plus minus infinity. And, what makes this kind of integrals difficult is the oscillation part, because it contributes less and less as you go further. And, what does it do? So you're right. The moment I go a little bit off, I put imaginary part to this z. So I go a little bit off the real line. If I go in the up, I put a positive imaginary quantity, then the one that's in the lower plane explodes of these two guys as the magnitude of z increases. And if I add a little imaginary part, then the other one decreases. So this object, as I look at it, I cannot close the contour either above or below, because, one of these terms will blow up.
Okay.
But then, I use a very simple trick. I just use one of the terms, like this one. And remember that the cosine is a real part of that. So that's...
Okay.
Now, the moment I have one of the terms, then I can close the contours. So that's what I'm doing. We have split the exponent here into an oscillating part and a prefactor, which, it just goes from, sine will go from 0 to pi. So the factor in front of r will change. So, here it's e to the r times small number, but for any angle, non-zero angle, minus r wins out. Up here, sine is just 1, so it decays as fast as possible. The basic thing, this part decays, and the magnitude of this one, when we take a real part, is 1. So that's how we get rid of the oscillation. We had oscillating integral from going plus to minus infinity, but now writing in terms of complex parts, the oscillation goes away because the real part just kills the oscillation. And we have a smooth integral where, this exponent varies, but smoothly we state that there is no great variation. I mean, this dies if r goes to infinity and sine theta is larger than 0. In other words, an integral 0 theta pi. And now, the endpoints, it's of order 1 with infinitesimal regime, so they don't produce any singularities or anything. So now we can close the contour in upper half plane. This is totally typical calculation you have to do in quantum mechanics and in electromagnetism when you're looking at wave scattering problems. And so now we have a contour. Original integral was on the line. There's no singularity because the poles of this are on the imaginary axis. Poles at minus IA and plus IA. So we run this integral, and now we added a zero by taking off and completing a contour in the upper half plane. Of radius r arbitrarily large. And now we use our Cauchy theorem. There's only one pole, this one in the contour. The other one is outside the contour, so it doesn't contribute. This integral on the contour is this part, but I have to subtract from the contour the half circle. So I have to subtract that part. But that costs me nothing because that contribution is zero for a very large circle. So residue calculus says, well, there's a residue, it's at this pole. So now the function, the numerator can be easily factorized in the form of two poles because that's quadratic polynomial. And we happen to know the answer, and we evaluate it at the upper pole. And residue means we have to cancel this pole. So this goes out. Upstairs, we just Z is IA. I squared is minus. So we get exponential up here. And downstairs, we just have to add IA and minus IA minus. Because this is minus, I get this 2 times 2A. I's cancel. That's good because this was a real quantity we were computing. And we get that this integral, which could have been some kind of, mean power or something, is the imaginary guy is just a real number. The one that I wanted to integrate is a real part of this one, but that just already happens to be real. And again, just exercising.
A lot of integrals.
Yeah, so what happens is I recommend looking at Arfan, Weber, and Harris. That chapter is quite good. It has lots of stuff in it. And you can kind of scan through it. And I'm working out few integrals from that chapter for you, just so you get a hang of how you do it. It's explained well. And it's a bunch of recipes of kinds of integrals you encounter. Just remember that they exist if you need to do them in some other context. I'm just giving you a little taste tasting tour of various things complex. I'm not proud. I hate doing this algebra in public, but hopefully if we do it together once and you keep asking me what am I doing, make it much easier for you to absorb that and store it in your memory. So here is another integral. It depends on two parameters. So there are two oscillations. So, when does this happen? There are two typical lengths in your problem. You're on some kind of lattice or two lattices stuck on top of each other, and you can think with one-dimensional. Two-dimensional graphene is a typical example of such integral. So you have something where there are two periodicities on a lattice, and they're somehow competing. So, one of these things has a period of 2 pi over b, and the other one has a period of 2 pi over a, and they oscillate differently. So we have a singularity here. So when you want to turn this into a contour, we have to take care of x squared. Now, these cosines or bx on a real line, they're bounded between plus and minus 1. So there's some two nasty oscillations that have beats against each other. So there's another envelope for these oscillations. But if you try to get off the plane, either one of them will diverge again for a complexified version going to infinity. So we do the usual trick. We write another integral where we replace these guys by IBC minus e to the IAZ divided by z squared. So as before, this is just identity. I've only changed on the integral itself and only changed the letter because the z on the integral doesn't have imaginary part. But I've used Euler formula to replace cosine and sine by a real part of a phase in two-dimensional complex plane. And now I can draw a contour, which I always have to verify, which avoids, again, the origin here. It has part excluding the origin, so principal part. And then I run on a big circle. And that contour, the only singularity is at the origin. So it doesn't have any singularity. So this contour is 0 because there are no poles inside. So how do I do it? I look at the real part of the principal part here. Now, by the integration, principal part is the sum of these two semicircles. And the outer semicircle, I've already proven a number of times, vanishes. So the only one that matters is the little one here. And these I can, for small, I'll be looking at very small z. So they have nice Taylor expansion. Which is just ordinary Taylor expansion of exponentials. They're correct for complex. Both of them, one has, they have different coefficients. There is z squared down here. And I know that I have to pick up a term, one of the terms is difference between these two parameters. The next term is the difference between the squares. Now, that's a pole, that's constant. But I remember that the only thing that contributes to a circle is the pole. So the only thing I pick up is the difference of these two terms here. And there was an I here and there was an I in front someplace. Well, the real part, yeah, just real part. An I will come from changing dz into d theta over d theta integral. So this goes away. And just get the difference, real part of a half turn, 2 pi I, going the wrong way because it's counter rotation. Residue evaluated at the origin, and we just get pi a minus b and this residue is 1, so that's it. And this will be a Zangwill type lecture because I can't do more integral. I cannot inflict more integrals on you. I just want you to feel assured that you know how to do them.